Okay, so couple of things before we start today. We're going to see something real, a gyroscope, or a top. I sent you an emails about tests and how they need to be handwritten. I mean, I think mostly all of them sent me an handwritten test, and I thought it was obvious from the fact that one of the bullet points says your handwriting needs to be neat, but just to make sure, I want to see your handwriting. I want to see you thinking on that paper. So I will specify that I want you to write with your hands what you do on your test. And then regarding issues with the first one, this is really the last day about anything that we want to discuss. I'm more than happy to do it today. From Monday on, I will be less happy to discuss test one, because if you haven't looked at it in 2 weeks, I think that means that you're fine. But so just wanted to clarify those things. So we'll see something. I have a few notes for me because this is going to get a little complicated. And so if you can switch to the camera here, I brought my toy, the gyroscope, which you can see this is the rigid body we're going to try to model at some point. It's a wheel. Of course, it's symmetrical. We're going to ignore the cage here. That is just a mount to attach it to different other toys like this base. Because every time we model something, we need to make assumptions. And the first assumption will be that the mass of this wheel is much higher than the rest, especially the cage, which is true. It is really true. So I'm going to spin it up and put it down here. And then we'll justify why we can model it the way we're going to do with the sketch there. But it's good to have a physical system to look at and try to see if we can justify what it does. I was just looking at what we studied, so I just need to spin it up now. So what you may want to start thinking is, once I spin this up, and of course the table, the room will be an inertial reference frame, the angular velocity of this object with respect to the inertial reference frame, I'm going to set it up here, right? It will be pointing, if I hold it and let it go, at the beginning it would be pointing in which direction? Direction of the spin axis, right? If I just hold it as I'm doing now, assuming that my hand is not moving, I'm just going to sit it there, that would be the omega. And then this is a symmetric object. So we're not going to discuss too much about principal axis coordinate systems and you know, how you can manipulate the inertia matrix, but you can imagine how this has a symmetric, how the spin axis is one of the principal axes for the body coordinate system, and then the other two would be in the plane of the wheel, right? So now this is spinning. I'm gonna sit it down here, try to hold it at the beginning, and then I'll let it go. I'll just give it an angle, and then it goes. And it starts doing this. And it will eventually spin down, so there's a lot of friction here. This is supposed to be a super precision gyroscope, but it's not that great. So in first approximation, what we can say is that the moment I put it down, the angular velocity was about the spin axis. You can imagine which direction was the angular momentum for something like this. Probably about the same direction. We're going to write it down. And then you need to justify to yourself, why is this object doing this? In other words, why is its angular momentum now changing? At the beginning, I grabbed it and I put it down here, and it was just pointing in one direction in the inertial reference frame, right? And then I let it go, and it starts doing this. So obviously, the h is not constant anymore, as you can imagine. Well, the other things that you start thinking about are, what are the forces acting on this object, of course. The center of mass will be at the center of the wheel. Everything is symmetric here. Again, ignore for a second the cage. The cage is just to make contact with the base. Center of mass will be there. There is gravity force acting there, and there will be a reaction at a point of contact, right? Those are the forces that are involved. And so somehow those forces are creating a moment that affects h. Otherwise, this thing will just, I put it down here, and it will just stay there, but it doesn't, right? So there is something creating a moment that is making it move that way. And we're going to try to find these equations of motion. But what can you tell me by looking at this? Well, gravity is obviously pointing down. There is nothing more to say about it. What can you tell me about this reaction here? Yeah, there is friction. There is all sorts of things happening here. But how would you model this force? And again, we assume that this is a point, right? That's what we're going to make assumptions here. That the contact occurs on a point. At that point, which we'll call O, which way is the reaction pointing? Do you know? Can you tell me anything about the reaction? Is it going to point towards the center of mass? Why not? What do you think? This is a thinking class. I'm going to do some calculations, but it's good to look at a physical object and understand that we make approximations and they help us understanding what's going on. This is, as you can hear, spinning down, but it's still doing the same motion. The only thing I can say is that this is a rigid body, and the third law of Newton applies to particles. When we said, at least the strong form, when we have two objects, two particles, and they exchange a force, that force, those two equal and opposite forces are going to be along the line of action, but this doesn't apply to rigid bodies. Third law of Newton doesn't say anything about rigid bodies. All we can say is that there is a reaction from the ground, this base, which can point in any direction. There is nothing telling us that it needs to point to the center of mass of this rigid body. It's basically the third law of Newton in the weak form, right? It's a reaction, it's just pointing somewhere. And it does make sense. If I spin it up again, let me just do it one more time. So we're convinced that h, the moment I put it down, the angular momentum is along the spin axis. Does it make sense? At time 0, when I put it down, omega is only in that direction. So when you multiply the inertia tensor times the angular velocity, and since we're going to use a body fixed coordinate system, which is a principal one, the only component that is retained is the I, call it ZZ, whatever it is, about the spin axis times the omega, which is about that axis as well. That's when I let it go. That's at time 0. But then, of course, things change, which means there is a moment due to which force that is making it move. Whoa. Think about h bar. I write h bar, that's what we'll do, with respect to the center of mass. If I use the center of mass, what are the forces that are going to give me a moment with respect to that point? Not gravity. If I use the center of mass goes through, gravity goes through the center of mass. It's the reaction. So that reaction is pushing it somehow in a random direction that I don't know, and has a moment with respect to the center of mass. So it does have an m bar which is non-zero, and if you recall the second law of Euler, which can be written with respect to the center of mass as d dt in an inertial reference frame of h bar is equal to m bar. There is definitely an m bar here that is causing this thing not to stay still like this. If this was in free space, like in deep space, and I did the same, it would just continue spinning in the same direction. It would do nothing with no other forces. But here there is a force. I put it down. There is a reaction from here, from the contact, that it's causing it to change h bar. So do we see this? This is a symmetric object, a body fixed coordinate system that has one axis along the spin axis. To any axis in the plane of this circle would be also a principal axis of inertia coordinate system. And we're going to try to solve the problem with respect to this inertially fixed point O. So this is the time that we can where we can switch maybe to this image here. Maybe. Can we switch to the screen? Thank you. Okay. So we are going to approximate this object with this representation at top, which is basically what we have. We are forcing the point O to be inertially fixed because I have that base. It's not going anywhere. This rigid body here is just telling me that I have something that has a symmetry about the spin axis. So it's just a representation. I could have had the same exact shape. And there is gravity acting on the body, and of course there will be a reaction here. And that's all I know. And I want to find the equations of motion of that object. So the first thing that I'm going to start doing is observing what I just said with a free body diagram. If this is my object, and now you understand why I prefer showing the image rather than drawing that. So this is my inertially fixed point O, and this is the center of mass. These are the forces. mg pointing down, and then some reaction, call it R, which is acting at the point O, and I have no idea which way it's going. It can be in any direction. If I want to use second law of Euler, which as we'll see will be sufficient to find the equations of motion, why? How many degrees of freedom does this have? It's not always the case that it's sufficient, but let's. This point is not going anywhere. So if you look at the rotation only, you're fine. There is a point which is always inertially fixed, right? So that's 3 degrees of freedom. Okay. So I'm going to try. Again, it's not always the case. It depends on which point I pick to compute moments. It's not always the case that using only one of the Euler's laws that I can find the equations of motion. This is one of them. As we've seen last time, it depends on what you do. And so if I want to use O, which is inertially fixed, let me write it here just to make sure that this is clear. O is inertially fixed. And what I am doing, I'm assuming that this room is an inertial reference frame. So the second law of Euler tells me ddt in n of h o n is equal to mo. And we agree that if we do this, we pick O as an advantage because that unknown reaction will not be part of the moment. There will be only gravity, which I do know, right? So now the things that I need to do, as last time, is, well, computing this moment. That's pretty simple, actually. But in order to solve this equation, I need to find HO in n. What did we say we do? Always, we start with kinematics, then we do the free body diagram, which I've already done, and then we implement the laws of Euler. Right now, I'm focusing only on the second one. So for this problem, if I only look at the second law, what is kinematics equivalent to doing here? What do I need to do? Very first thing. Find h bar. So why? Because I know that HO in n is going to be equal to h bar n plus RO minus R bar cross with what? M VO in n minus V bar in n. And we said this is written with respect to the center of mass in a body fixed coordinate system because there are tables that tell me what that inertia tensor is. And so let me start writing this. I have to pick what I'm going to do here. So if we can go back to this image, if that's okay. So I'm going to do something a little strange here. I'm going to write all my equations in a coordinate system which is not body fixed because it makes writing them easier. You can do whatever you want. You pick your coordinate systems. These are all choices. It does happen in this case that it makes things easier. So first of all, I need to parameterize the motion of this. In all the problems we've seen so far with a single rotation, you would have that angle theta, right? That's what we've done so far. This is a 3-dimensional rotation. So we've talked about ordered angles. How about I choose a sequence of ordered angles that would be my parameters, and I want to find differential equations in terms of those 3 parameters. Stop me anytime if the line of thinking doesn't make sense. So I have the inertial reference frame, the coordinate system which is fixed in that inertial reference frame as the origin at O, as a big EZ axis which is pointing down as the gravity acceleration, and then there are 2 more axes, EX and EY, big EX and big EY. When I parameterize the orientation of a rigid body with respect to a reference orientation, so the reference orientation would be big EX, big EY, big EZ, what I am doing, I am assuming that the object was aligned with big EX, big EY, big EZ, and then it went to its current position, which I'm representing with three angles. So in this particular sequence that I'm doing here, which is a 3-2-1 Euler sequence, I assume that this symmetry axis was actually sitting on the EX axis at time 0, or at time 0. That's the reference orientation. And then it goes to a generic orientation, but a 3-2-1 through a 3-2-1 rotation sequence. 3-2-1 means that the first rotation is about the EZ axis of an angle psi. So EZ and the new axis called PZ are the same because the rotation is about that axis. Big EY becomes PY, big EX becomes PX, and there is this rotation psi. Okay, that's the first rotation, the 3 rotation. Then I do a 2 rotation about the second axis, so the PY axis, which corresponds to the new QY axis, which is this theta rotation, which will bring the gyroscope up and change PX into QX, and what else? And PZ into QZ. That's the second rotation. And then the 1 rotation will be about the final EX body axis, or QX, of an angle phi, which will change QZ in the body axis EX, and where is it? And QY in the body axis EY. It is hard to visualize, but I never said that these things were going to become simpler along the way. So that's a 3-2-1 rotation. That's exactly what we're seeing. It's just that now one of the axes is pointing down, but it shouldn't make any difference. So I am looking for differential equations in terms of these 3 angles. That's what I want. But I'm telling you that I will project that equation, every piece of that equation, not in the small ex, little ey, little ez coordinate system. I will use the intermediate one, which is little qx, little qy, little qz, just because it makes, first of all, the computation of these a little simpler, the moment with respect to the point O, and because I can do it, because there is a symmetry in this problem that allows me to do it that way. So if we go back to the board, what is the first thing that I have to do here with h bar? I know that h bar is some I, tensor of inertia with respect to the center of mass of the body B, dotted with omega body with respect to the inertial reference frame, right? But I do know that this is can be written as some, I'm not going to look at tables here because I don't know exactly what shape I have. So I'm not going to write expressions for the moments of inertia. I'm just going to leave them as parameters. Some Ixx bar. If I was in the body coordinate system, you guys have that always with you. You can look at that image. I don't need to switch back and forth anymore because you have it there. And I think I put it on canvas too. So this would be the inertia tensor if I were using a a body fixed coordinate system, right? Plus y I bar, I'm sorry, zz, ex, circle cross ex. Nothing else. It's a symmetric body. The symmetry axis is definitely a principal axis of inertia. And then since the section is circular, it doesn't matter where I cut that object. It's always a circle. It doesn't really matter if I'm picking a body fixed coordinate system, which is actually rotating with the body, or something else like px, py, that doesn't necessarily need to be fixed with the body because it's a circle. Do we agree with that? So what I'm saying is that I can rewrite this inertia tensor using the p's instead of the e's. It's going to be the same. So let me see, qy, yeah. So, I'm sorry, did I say q? Yeah, I said I was going to use the q axis, right? These are the q axis. That's the last rotation. Q, x, q, y. That's why I brought my notes. There's a lot of axes here. Does it make sense? Do we agree that if I write something, if I compute these i's with respect, of course the z is not going to change, but if I switch the little ex, little y for something which is in the same plane, given the section and the symmetry, is going to give me the same results, right? And so I can write this in the same exact way as nothing is really going to change. Ixx bar, what did I call that? Qx now, yeah, it becomes Qx, circle cross Qx plus y bar, I bar yy, q, that's qy, I have an error here. Do you see that? This is wrong. Go back to the picture. The way I picked the axis, Qx is the symmetry axis. I'm sorry, it's not the Z one. Make sense? Okay, so yes. So little x and qx are the same thing, and then these are the ones that I'm changing. It's actually y and x, but again. Okay, y bar zz qz circle cross qz. So I'm going to work with this q axis. Oops, I don't know what's going on with the image. It did that last time. Not good. That's okay, we'll survive.
Okay, I can switch the other to take this one back if you want to it.
That would be nice to have it somewhere.
I'll put it on that one.
You don't need to put it on video, yeah, it's okay. Thank you. So, okay, so I have a way to write the tensor of inertia in that coordinate system Q. Then I have to write what? Omega. I need to find it. That's actually nicer if we have it there. Omega of the body with respect to n is what? Now things become a little entertaining here. My parameters are those three angles. I'm going to start writing things. I do 3, 2, 1, so I go one rotation at a time. We've done it before. The first will be psi, so I have psi dot about which axis? PZ, for example, or EZ, it's the same thing. Remember, I want to express everything in Qx, Y, Z. So eventually, these will have to be expressed in that way. Second rotation is about Qy, nice, that's already in the correct one, and it's a theta dot. Make sense? If you get lost here, it's fine. That image is a 3D rotation image. So, and the last one will be the phi rotation, phi dot, about which axis? Qx. Okay. So the only one that I don't see being a Q here is this P. What is PZ in terms of the Q coordinate system? Can you see it? PZ is contained in the plane of QZ and QX. Remember, the second rotation is about the QY axis and brings PZ to QZ and brings PX to QX. So I can write PZ as cosine of theta QZ minus the sine of theta QX. Agree? Should probably start drawing some axes here. This will be your QX. This will be the plane QX, QZ, right? And basically you have this PZ, which is down here. And this is theta. That's what I'm doing. So PZ is cosine theta QZ minus sine of theta QX. Okay, fine. Let's rewrite this with this knowledge. This is equal to psi dot cosine of theta QZ minus sine of theta QX plus those that don't really need to change because they are already in the right coordinate system. So if I reorganize the terms, I get that the angular velocity of the body with respect to the inertial reference frame, so the angular velocity of that toy with respect to the table is, let's see, I have a phi dot minus psi dot sine of theta qx. And then I have a theta dot qy. And then I have a plus psi dot cosine of theta qz. And I will have to dot this with the inertia tensor, which is expressed in the same coordinate system. Cool. OK. Let me write it here because we're going to need to keep it somewhere. Sine of theta qx plus theta dot qy plus psi dot cosine of theta qz. Guys, is everything clear what I'm doing here? More or less? I'm doing what we done last time with a planar problem. Same, the steps are the same. Computing h bar, and then I will move it to another point O, and I will do the derivative and compute the moment and write the final equation. The difference is that now this is a 3D rotation, so everything that I'm going to write, every vector that I'm going to write, starting with the angular velocity, and then tensors, so the tensor, and all the other vectors will have to be functions of my parameters. As in the last time, everything was a function of the theta angle. In this case, it needs to be a function of 3 angles, because this thing is actually free to rotate in 3D space. It's only more elaborate, geometrically speaking, and has more variables, but the procedure is the same. Stop me anytime, OK? All right, so I have this angular velocity here, and if I and you really want to go back to this image and do your crazy movements with the hands and figure out the rotations to convince yourself of what's going on. So h bar in n, let's do it just right away. If I dot this inertia tensor down here with the angular velocity, what do I get? I get ixx bar multiplying this, right? Qx plus I, what is that? Yy bar theta dot Qy plus some yzz bar psi dot cosine of theta Qz. Agree? Disagree? I need to check here. I don't want to make mistakes. Yeah. I don't think I even have it. Yeah, well. OK. Well, but that's only h bar. I'm not done. I am working with respect to O. So I need to figure out that extra term, right? What do you want to do? What is R O minus R bar? R bar would be RC. That's the center of mass. Oh, no. What happened? We lost the image. I mean, I have it here, but.
The computer just fell asleep, that's all.
Oh, that's it?
Yeah.
And do I need to log in again?
Yeah, I should just control it with the edge pop.
Oh. Other user? I don't even see what I'm doing. But how can it show? Oops. That's not showing what I had.
I'll grab one of the guys for you.
That's fine. I mean, I think you guys have kind of, hopefully. Can we go back to my laptop maybe somehow?
Oh, that's where the picture was?
No, it wasn't. I mean, yeah, it was. Yeah.
Okay.
Yeah. It's on the laptop. Maybe my laptop went to sleep. Hold on a second. Yeah, it was my fault. Don't do anything. I'm sorry. I have to touch it every once in a while. Okay, so what is, so that's the position, remember the origin is down there, and I'm using the q-axis. The origin is the point of contact, so RO is obviously 0, and that's minus R bar. The length is L, so this is minus LQX, correct? So that takes care of this term here. And then what is VO minus V bar? And every time you think I touch my mouse here, just in case. It's showing all over the place now. Okay, so what do you want to do? Do you really want to compute VC? I mean, do you need to do that? Do we have something that we can use? These 2 points, well, the first one is 0, right? This is an inertially fixed point. The second is not. Obviously not. That thing was moving. So how do you want to compute this difference? There's one way, you can write just one relationship here, and then you have to plug in all the components. But we do have a property that relates those two. We're good. I can be on the screen. That's fine. Thanks. These are 2 points that belong to the same rigid body, right? What's the relationship? You have to use the few things that we know. Just create your cheat sheet if you want, cheat sheet. Yeah, and then unfortunately you have to compute the cross product of these nice formula here with this tiny vector. So we can do it. Let's try to do it once without making too many mistakes. Okay, the first one is a qx with qx, 0. Okay. Then I have a qx cross with qy. There's a qz with a minus. So minus L theta dot qz. Correct? Am I doing it the right way? It's the opposite way. Yeah, it's this cross with this. Plus. Thank you. And then qz cross with qx. That would be qy with a minus. This is minus qy. Right? Minus L psi dot cosine of theta qy. Make sense? And then I will have to cross these with that. I know. At some point I will skip some steps because I don't think we have time to do the whole thing. And it's a bunch of cross products, but I want to show what are the steps that you need to take. Let me see. Can I give you this?
Wait.
What? What's wrong?
We're crossing that with that, right? That's not
These with these.
Yeah.
That's what I have. Yeah. So let's do it. Let's do the R0 minus R bar cross with M V O N minus B bar. And it shouldn't be too much. So it's this with this. Qx cross with Qz minus Qy with a minus plus L squared theta dot Qy. Agree? Qx cross with Qy. Qz. There's 2 minuses, so it's still a minus.
Forget the M.
Don't forget the M.
Yeah.
There is the M at the end. Yes, thank you. I always forget the M. But I did forget what I was doing now. Qx, Qy is Qz minus Qz, so it's minus L squared psi dot cosine of theta Qz times the whole thing times M. So we will have this HO. I have to add all the pieces together. HO, so if you allow me to do this, HO is this, which was H bar. This was H bar in N, plus this vector down here. M L squared theta dot Qy minus M L squared psi dot cosine of theta Qz. Before I raise it and miss anything, looks like it's right. Excuse me? Make sense?
When you cross the second term, the negative.
So the second term is Qx crossed with Qy gives me a Qz, but there is a minus here, minus Qz, and there is a plus. Thank you. Okay. Anything else? I want to start grouping things together here. I think this is good. If I collect the same Q's together, I get, let's see, well, this should not change. And why doesn't it change? Because I haven't really changed that axis. I'm not affecting it. Okay, with the moving, this is the transport theorem, but I'm basically moving, not the transport theorem, I'm sorry, the parallel axis theorem, moving on another point O, which is along the symmetry axis. That's what I'm really doing here. So Qy is, what does it have? Theta dot is in common, that's great. I can just put it outside. So I have I y bar plus that ml squared theta dot Qy. Does it sound familiar, this ml squared, the parallel axis theorem, that you take the mass and you move it the distance L? Yep. Y bar zz plus, same thing, ml squared. Makes sense, there is a symmetry here, and they have the psi dot cosine of theta in common, Qz. Now, just to make my life simple, I can just stop calling these things I, ZZ, I, etc. IYY and IZZ will be the same, given the symmetry, right? They should be the same. So I can really call these two quantities here with some other name, I1. It's a constant, I don't care. I'll call these I0 just to make my life easier. So my final HO in N is equal to some I0, it's a constant, phi dot minus psi dot sine of theta Qx plus this I1 theta dot Qy plus I1 psi dot cosine of theta Qz. Okay. That's HO in N. I need to take its rate of change in the inertial reference frame. Suggestions? So let me just rewrite it up here. This is not needed anymore. The omega I want to keep it, and the HO, of course, I want to keep it. While I write this, how do I get the rate of change of this in the inertia with respect to the inertial reference frame? How do we do it? You really need to tell me how we do it. At this point, all pieces must come together. What is HO bar? HON? What is it in general? It's a scalar? It's a vector. Okay. In which coordinate system is it expressed? In some basis q, x, y, and z, which is fixed to some, of course, you're imagining here coordinate reference frames, right? So this qx, qy, qz is a coordinate system fixed in some q reference frame, right? Go back to your notes about Euler angles. Every rotation we've taken, we have defined the reference frame. The axes undergo a rotation, there's a new reference frame. Then another rotation, there's a new reference frame. So let's call that Q, capital Q, the reference frame where that basis is fixed. So what do? I don't want the rate of change of HO in Q. I want it in N. Which are the axes, the basis that is fixed in N? The inertial. The big E's, right? Okay, I don't see big E's here. What do you want to do? Really, you want to do that? Transport theorem. It's a vector. It doesn't matter how ugly it is, how long it is a vector. If a vector is expressed in a reference frame which is not the one in which you want the rate of change, bling, transport theorem. That's what you do. Because you do have almost the angular velocity that you need. Because this is going to be equal to what? D dt in that Q reference frame of the same vector, of course, plus the omega of that reference frame respect to the inertial one cross the vector itself. And this is probably the point where I'm not going to do the calculation. I'll just give it to you. But I need you to figure out a few things. This first term will basically mean taking this expression of HON and derivating the components, right? Phi double dot minus psi double dot sine of theta minus psi dot theta dot cosine of theta, theta double dot, etc., etc. You don't change the q's. The second term is what takes into account the fact that these q vectors here, basis vector, are not fixed in n, so I have this extra term, right? We've seen it several times. Now, the only thing that is really missing here is this omega. I don't know what that is. Do I? I have the omega of the body in n.
Well, isn't like the omega of the body in n equal to this plus something like q to body?
I would almost say that it's probably that you can get it from the omega of the body less something, minus something, rather than adding something. What have I done?
Something equals that. So
Right. Because this is, I have one more rotation to go from Q to the actual body. And my sequence 3, 2, 1 was designed to go to the body, right? A body fixed coordinate system. And so the Q reference frame is the frame where I am before I do the last rotation. What is the last rotation? Phi, right? So if I take this and I just set phi dot to 0, that's my angular velocity. I don't have the last rotation. I just go to the same line of thinking that led me to compute this, just I don't do the last rotation. Does it make sense? So when I build this omega qn, what I do is, how do I get to q from n? From the coordinate system which is fixed in n, and then I go to the coordinate system which is fixed in q. Well, I start with a 3, 2, 1, well, 3, 2. I don't do the 1. I do a rotation about pz, so same thing that I've done before, psi dot pz plus theta dot, what was that, pq? We're talking with q, right? Yeah, qy. And I stop here. But then I need to express pz in q, etc., etc. But I've done it already. So I take that and I just remove the phi dot. I don't execute the last rotation. Make sense? Okay, so I do have that, and if you want, I can write it, but it's really not that critical. It's a minus psi dot sine of theta q x plus theta dot. I will send you these PDF notes, so you guys can look at the details if you want. But we're almost there. I'm not going to do this because we don't have time. What you need to do is take the time to go through the derivative of this, do the derivative of each single term here, as I said, theta double dot, etc., plus you add this cross product of this vector with this vector, and it's going to be a lot of fun. Yes, 5 minutes. I'm going to give you the final result that you should get. Once you put it all together, your ddt in n of h o n should look like I0 phi double dot minus psi double dot sine of theta minus psi dot theta dot cosine of theta, and this is on the qx direction, and then I have I1 theta double dot plus I1 minus I0 squared cosine of theta sine of theta plus 0 dot phi dot cosine of theta qy plus it's a long one. But not impossible. It just takes time to do the cross product. That's all really you have left. Phi dot, and this is q, z. Anyways, that's what you should get. And this is equal to m0, mo, which I still need to compute. And that should give you an idea of why I usually do problems where the rotations are now more than 2, because things get complicated. It's not impossible at all. It becomes extremely boring doing the algebra. That's all. So the only thing that I really am left with is finding the m of what? Which force? Only the gravity is what I care about, because the reaction in O doesn't matter. So what is MO? It's going to be R bar minus RO crossed with mg, right? That's all I have. This R bar minus RO is something we computed before. There was a minus, so this is probably a plus. LQX. That's it. And then this is crossed with mg. Gravity is along PZ. And this is the reason why I picked that strange coordinate system, that intermediate coordinate system qx, yz, because if I had done the actual body axis coordinate system, which is also spinning, it will make computing this a little more elaborated. But here I can easily do the same that I've done before. PZ, I know what that is. In terms of q, it's, what was it? PZ is cosine of theta qz minus sine of theta qx. And you do this. And you put it all together, and this will only have a component about the second axis, the qy. You can see why. I mean, this will go to 0, qx crossed with qx. Qx crossed with qz will give you a qy direction. So your equations of motion will be first one equals 0, second one equal whatever you get from this, which is, I can give it to you, I think it's a pretty short expression. What is it? Minus mgl cosine of theta qy. That's it. So second equation of motion is that equal this expression, and the third is the last expression equals 0. And then good luck integrating those equations. But that's all we wanted to compute. So this was what happens when you deal with a physical system where we have made assumptions. I have neglected the mass of the cage. I am assuming that the contact occurs at a point. That's a bunch of points touching each other there. I have made simplifying assumptions, and still I get this. But the line of thinking is the same. There are two laws, Euler's laws. You need to write h bar. Well, the first one is compute the acceleration of center of mass. We didn't need that here. But for h, in particular, h bar, just go there. You need omega, you need the inertia tensor, if the motion is complicated, unfortunately, it will become a function of three angles. Otherwise, it will be simpler. It cannot get worse than this. Okay. We'll see you on Friday, I guess.